Right. Okay. Well, very happy to be here. Thank you for having me. It's great to be up to Edinburgh again. So I'll talk about all things green computing. I don't know what everyone's background is, so hopefully it's not too boring. How do I do that? Here we are. I always have this slide at the start to say, I'm not here to say high performance computing, AI is terrible. My background is in machine learning and statistics, in biology. So there are no doubt it helps a lot of amazing discoveries. Where it is interesting for the topic of today is it also helps in the domain of climate change. So, you can use AI to optimize energy grids. There are amazing things in biodiversity to identify the best place of ecosystems to support, to regenerate biodiversity and things like that. So it's out there, not denying any of the benefits. Problem is, it comes at some cost. So the link between these two images may not be immediately obvious, but it turns out that globally, data centers have about the same carbon footprint as the American commercial aviation. 126 megaton of CO2 if you're interested in numbers, but mostly, same order of magnitude. So far from being negligible. And if we look in the UK, it's about 4% of the energy grid goes into data centers. So that doesn't sound like a lot, and that's an argument you'll often hear. Am I very loud, or is it just, no? No, okay. It just comes back very loud here. That's fine. So 4% doesn't sound like a lot, and often you'll hear arguments saying, well, it's only 4%, do we really need to care about it? Let's look at Ireland. Ireland was really keen on getting big tech companies. I don't know about data centers, but they're really keen, so they gave them huge tax breaks. And that worked really well. They all moved there. Now, data centers use 22% of the energy grid. That's more than all the urban dwellings. So all the private home in urban settings use less energy than data centers. That is quite scary.
Yes.
But the reason it's really scary is it means they don't have electricity anymore. They can't build more homes because they are data centers. And they can't even build data centers because there are too many data centers. So you'd say, okay, fine, they kind of have all the data centers they need. Not quite. So they still build them. The problem is they can't connect them to the main power grid because the grid can't take it. There's just not enough power. So what do? You build your own gas power plant in the backyard. And so that is from March 2026. So, last month, they announced these brand new data centers that can't be connected to the power grid. It's entirely, so they sell it as an off-grid data center. That sounds like hippie and sustainable. It is not. It is entirely powered by natural gas. Now they're having slight regrets about that strategy, and I think it's becoming less financially viable with the Iran war. But still, entirely fueled by natural gas, which is, you can imagine in terms of air pollution it's in West Dublin. I mean, it just comes with terrifying consequences. So this idea that, okay, maybe we hit a limit for data centers, but then we stop, doesn't really apply. We just keep building them. What they can't build is new homes. All right. This couple of numbers to keep in mind. This one's interesting, 45%. That's what the ITU, which is the International Telecommunication Union, so the trade body for the digital sector, said we need to decrease the ICT sector, so roughly the digital sector, carbon footprint by 45% by 2030. Importantly, they're not saying we need to do 45% more with the same energy as today. They're saying we need to decrease its carbon footprint by 45%. And that's a trade body, right? That's not a kind of friends of the earth kind of pro-environment society. So it's probably a conservative estimate. And finally, I'm probably going to I'll try to not to throw too many carbon footprints, but especially in the next few slides, I'll have some examples. So to put them in context, you can use that as a kind of baseline, 2 tons per year per person. That's the target if we want to keep global warming under 1.5 degrees. I mean, admittedly, we failed on that already, but we can hope to get back to that. An average person in the UK is maybe closer to 7 or 8 tons of CO2 per year. But 2 is what we want to benchmark against. So let's take a few examples from AI. This one is a bit older, 2022, but they looked at different models. Problem is, companies like Anthropic or OpenAI are really good at keeping their models closed, so they had to look at GPT-3, which was the last open model from OpenAI, ancestor of ChatGPT, and they found that training the model once doesn't include research, doesn't include retraining. Training it once, 550 tons of CO2 to train that model. right? If we compare it to the 2 ton per year per person, that's quite a few people's allocation. And the point of that paper was to show that different models could actually have much lighter footprint for similar results on real world cases. But recently, some companies have tried to look at that a little bit better. So Mistral AI, you're probably familiar with them. They are kind of the French attempt at OpenAI. They're building their own model called, not very inspiringly, Large 2, but that's the name of the model. And they've released an assessment. It has limitations, it's not perfect, it lacks transparency, but at least it exists. And they looked, it took 18 months to train the model, really, including the research and all the training and all the development. And over that 18-month period, 20,000 tons of CO2. That's what it took. 280,000 cubic meters of water consumed. And the last metric is kilograms of antimony equivalent, which is abiotic resources, so rare earth metals extractions. The unit is kind of a bit barbaric, but the planetary boundary for that is something like 0.03. So 660 is actually huge in comparison to what it should be. Anyway, 20,000 tons of CO2, that's enormous, right? That's like 10,000 people allocation of annual carbon footprint just to train that one model. So that's that. All right, so computing is not free, clearly. But if you are lucky enough to be in a reasonably well-funded university, like Edinburgh or Cambridge, kind of looks like it. Not if you use the cloud, but if you use institutional data centers, like if you use institutional compute here, you don't really pay for it, or if you pay, it's very small cost, so it's probably your PI. And even if you're the PI, it's not actually a lot of money that goes into that, and it's money that's easy to repurpose from other things. So really, it looks like we can do compute for free, which is actually good. That's why, the fact that we don't have to do everything on cloud is a big reason why we can compete so much with industry on so many sectors. If we had to run everything on the cloud, it would be just financially impossible. So I'm not saying we should put enormous financial costs on everything, but it does. The problem is if there's no incentives not to waste something, then, I'm sure you all have examples of compute where you just, well, it doesn't really matter. No one's using the servers at the weekend. We may as well kind of burn it to create cat pictures. When I started working on that, I did it from the Department of Public Health in Cambridge because I was and I'm still based there. And I felt like, well, we're trying to cure cardiovascular disease, and a lot of it comes from climate change and air pollution. And I'm doing that by training AI models, which are contributing to the problem. And I had a little bit of an existential crisis over a weekend. But that's something we want to keep in mind. Right. I'll try to quickly go through this, well, not so quickly, we still have some time, but go through these three aspects. Break down the environmental impacts of AI and computing in general, talk a little bit about what we're doing in Cambridge, and then what can we do about that. So I really like this quote. I can't, for the life of me, I really can't find who said it. I remember reading it somewhere. I didn't invent it, but no way to trace that back. And they just said this thing of how data centers are where the cloud touches the ground. And I mean, you're probably all computing adjacent people here. The number of people who think the cloud has no physical reality is deeply disturbing. And I've reviewed papers where they said, move your data to the cloud so then you don't have to use hard drives. And I was like, where do you think it's? Anyway, lots of people think that, it's the cloud and it's kind of all light and in the sky. And we have to sometimes bring it back to, it has very much physicality there, and it comes with environmental impacts. So there are lots of ways to look at it, and sometimes that makes it a little bit difficult. And I'll try to break it down a little bit. So the first way to think about it is what we call embodied footprint. Embodied footprint comes from manufacturing the hardware. So it's not using it, it's the extraction of raw material, the manufacturing in the factory, and then disposing of it at the end of the lifetime. So that's everything we kind of put together as part of this embodied footprint. This paper that is just released recently is both interesting and terrifying. If you're a chemist, you're going to find the heat map interesting. If you're not, just ignore it. They looked at GPUs, and they said, OK, how much GPUs are used to train GPT-4? They found it's nearly 9,000 GPUs. And I don't mean you need to use 9,000 GPUs at a given time. You start training, obviously you don't do it like that in practice, but what they imagine is you start training on GPU number 1. You use it for its entire lifetime until GPU number 1 is just burnt and unusable anymore. And then you replace it with GPU number 2. And you do that 9,000 times. So basically, it consumes entirely 9,000 GPUs to train the model once. Obviously, you do it in parallel, and that's a little bit different, but that's the same idea. And that generates 7 tons of toxic elements because then you need to dispose of these GPUs, which is a little bit terrifying. This is Baoteng Steel and Rare Earth Material Factory in Baotou, Mongolia. This is not a lake. This is a completely artificial lake surrounded by refineries that basically process rare earth material for digital hardware. So it's one of the absolute core of what makes digital possible and the whole manufacturing process possible. They have a lot of waste, so they created this lake. And if you're interested, you can check out this BBC article, and the journalist who went there said, when you imagine like post-apocalyptic worlds, that's basically what it looks like. Just complete e-waste being, complete waste from electronic manufacturing being disposed of. And these embodied footprint, we don't see them. They're not related, they're not here most of the time because manufacturing doesn't happen here. Electronic waste is not disposed of here. But they very much happen because of the hardware we use, so we can't completely ignore it. If we go to the other end of the spectrum, once we've manufactured them, used them, then we need to dispose of it. There's this, again, rather depressing report from the World Health Organization that estimates that over 80% of the 50 million tons of electronic waste produced each year are basically processed by what they call informal waste workers, which means dump sites. This report was particularly about children, as you can imagine, operating with open batteries and opening up computers and TVs with no protection is not terribly healthy. So they kind of break down absolutely horrific health impact. But the main problem is we are terrible at recycling these electronic devices. And so actually a lot of it that gets produced ends up in dump sites. Again, not here, usually in low-income countries. So that's this idea of embodied footprint we need to think about. The other thing is we tend to only think about carbon, and I'm guilty of that. All the numbers I've given you so far almost are all tons of CO2 and greenhouse gas emissions, and that's obviously important aspect, but not the only one. And a useful framework to think about are these planetary boundaries. So they've been designed at Stockholm University. And they look at, so it's a little bit small. I should have zoomed in on that, but 2025 is a bit of a celebration. We managed to cross 7 on the 9 boundaries, and they're just a way of saying if we stay within the planetary boundaries, so within the green part, we don't leave the Earth in a worse state at the end of the year than it was at the start, right? So we don't disturb the system to a point that it is not able to recover anymore. When we start crossing planetary boundaries, we disturb the system so much that it can't bounce back. And so you've got the climate change on the top left. Climate change is greenhouse gas emission. So that's, can you see my mouse if I move it here? Yeah, here. So that's climate change, that's greenhouse gas emission, that's fine. But you see all the other ones have nothing to do with that. You've got biosphere integrity, land system change, freshwater change, biochemical flows, ocean acidification, which is the one we've finally crossed in 2025, atmosphere aerosol loading, stratospheric ozone depletion, and novel entities. And so basically, it's a really useful framework to remember that reducing greenhouse gas emission is great. It can't be the only goal, because if your solution to reduce greenhouse gas emissions makes all the other boundaries explode, that is not actually achieving the kind of sustainability we need to think about. Right. All of that to come back to the more obvious stuff. What's the operational footprint? And that's the impact of actually running models, running computers. And that's quite straightforward to estimate. You do the product between how much energy you need. That just depends on your hardware and your software. And then what's the carbon footprint of producing that much electricity? And that broadly depends on where you are in the world. And Scotland is going to come out very well out of that, you'll see. So if you're interested in that, there's this brilliant website called Electricity Map. You can go and check out. You can see for all countries the breakdown of the energy supply. You can see they put arrows between countries. You can see where it's going. I mean, it's a great website. You can, like, if you're a bit nerdy, you can spend hours on that, just like zooming on different countries and stuff like that. So, but you can see vast differences, right? The scale goes from 0 to 1500. Australia is something at like 800 or 900 grams of CO2 per kilowatt hour of electricity. The UK will be at 200. So, you can multiply the carbon footprint of the same task by a factor 100 easily between two different locations. In the UK, we've got something that is even more granular, which is put together by the National Grid. And that's this website. So if you go on there, you can zoom in by region. This screenshot was just a lucky one I did one day for a talk, but actually I managed to do the one screenshot where Cambridge is actually in the green area, because normally east of England is always kind of part of the south, which is yellow, but that day, so now I'm just keeping it. I'm never getting rid of this screenshot. Scotland is usually green. You've got a lot of winds. But so zooming in, I had to take another screenshot today, so you can see that's a bit more typical of what a normal day looks like. Scotland, actually virtually zero, because almost all the electricity comes from wind. East of England, we're at 111 grams per kilowatt hour. And so that's kind of interesting to see the different flows. And that's actually a real problem we've got in the UK, is we actually produce enough renewable in the year for most of the UK, but we lose about 12% of it because we have to turn down wind turbines in Scotland, because we're not actually able to take all this electricity from Scotland and bring it to the south of England where most people live and actually need it. So that's a bit of kind of wasted renewable, so they call that curtailment. It also costs a lot of money because you have to pay the wind farm to turn off, so it's kind of a lose-lose situation. Right. Understanding how do we estimate this power we need based, you're saying I'm training an AI model, how much power do I need to train it? You can measure it, but it's difficult, and you don't always have access to the machine. So if you want to estimate it, you can break it down to fairly simple elements, and I promise it's the only equation in the talk. It depends on the running time, so how long your task runs for, quite intuitive. For power, you can focus on two components, which are the processor, so your CPU, your GPU, and the memory you use, so live memory. And then you need to take into account data centers overheads. So it's normally done with this metric, which is called the PUE, power usage effectiveness. It's a very simple metric. It's the ratio between all the power going to the facility, to the data center, divided by the power that actually goes into IT equipment. So you want that as close to 1 as possible. And it's just a way to measure, so this PU is just a way to measure overheads, which is mostly cooling, right? It takes electricity to keep the computers nice and cool. Again, maybe not so much in Scotland, but if you're in a warm country, it does. Anyway, so you multiply all of that together and it gives you an estimate of energy usage. I'm not going to go into the detail, but very happy to take questions on that later. Now, not everyone wants to write the formula and do the math, and that's very fair. So there are different approaches you can take and tools that do that for you. And there are broadly 3 ways of thinking about it. You can use an online calculator, a bit like a flight calculator, saying I'm flying from Edinburgh to New York. What's the carbon footprint of that? You can do that for your compute. You can put packages in your code that basically act like trackers. So you put them in your code, they will track what you're doing while you're doing it, and they will produce a little report at the end saying the carbon footprint of the code you just ran was X grams of CO2 or something. Or you can have monitoring tools directly embedded on the computing infrastructure, so directly on the servers or on the HPC, tracking what you're doing and giving you reports. So if you're interested in that bit, just because of time, I'll review some of the tools, the one we build in particular, but if you want the pros and cons of the different approach and everything, you can check out these 2 papers. So we started this Green Algorithms initiative early 2020, so over 6 years ago now. And it really started as just a tool, just this online calculator I'll show you in a minute, because there was no easy tool for researchers to understand the carbon footprint of the compute they were using. And the project has really spiraled now, working on policy and different activities, but keeping this core focus of saying, how can we enable researchers to understand the impact of their work so then they can make informed decisions? We're not saying we shouldn't do compute for science anymore, but if we provide information that says, if you knew that generating this cat picture was your entire yearly allowance of carbon emissions, maybe you wouldn't do it. Unless there's a great benefit, you think, of generating that cat picture, and then maybe you do it. But you need the information just to make these informed decisions. So the first tool we built was this online calculator. It's still working well. It's still online. You go on there. You say my code runs for that long. This is the kind of hardware I'm using. This is the kind of this is where I am in the world. You can customize if you know. particular parameters, otherwise you leave the default value, and that props up values of energy usage and carbon footprint. So it's quite straightforward to use. You don't need to plug it to anything. It doesn't matter what programming language you use, and that was really the intent behind it. So we actually have some quite cool upgrades coming up in the next few months. Last year, what we did was to release an AI version of that. So on top of there are now two panels, the classic one and the AI one. The AI one works the same way, except you can put both training and inference side by side. So you don't have to actually use the calculator multiple times. And also for the inference mode, you can have this, what we call this continuous inference. So like a chatbot typically, where you don't do like the old-fashioned where you use your AI to make predictions on a database all at once, but rather you have to make inference every time someone asks a question for it. So it's this like not bulk inference, but a more continuous one. So it kind of deals with all of that nicely. And then I got to the point, so a few years ago, I was writing my PhD thesis, and I was like, really don't want to be doing that. What else could I be doing? And I thought, the calculator is great, but if you run simulations 100 times, it gets a little bit tedious to use the calculator manually 100 times and save the value, right? That just doesn't really work. And I thought that would be so much better. Everything I do on the HPC gets logged there because I get charged or my lab gets charged a little bit. So could I just pull the logs and get the calculator to automatically do the math based on everything I've done? It turns out you can. So I did that. We called it Green Algorithms for HPC. It puts this uglier but more granular report out, which is a bit depressing sometimes. It gives you the carbon footprint of failed jobs, which is not great. I mean, it's great to have it, not great to see it. Things like memory over allocation or things like that. So it prints out all these metrics. And actually now you can get a prettier like HTML output. But that's still a little bit tedious because individual users need to install it and then use it. So we're like, okay, where can we go next? The obvious next step is to have everything installed on the HPC, not just using the HPC for the logs, but actually have an entire dashboard that users can just, a bit like the clouds are doing now, where they have this cloud that, if you use Google Cloud, for example, you get some magic numbers. You don't really know where they come from, but they tell you the carbon footprint of the jobs you've run there. And so we've been working for a while on adapting that into a dashboard. Navira Kamal, as a research software engineer in my team, has been at the forefront of that. And basically, it's this kind of neat little tool where it's installed on the HPC for all users. So you can imagine it on like Edinburgh University if you have a central computing infrastructure. And then as a user, you log in, you see the carbon footprint of your jobs over time, breaks down by metric. You can also see the impact of failed job. Stick with that. You can also see it aggregated by like different groups in your department. So you have different levels. And yeah, if you want to play around, there's a prototype online where you can basically, it's mock data, but you can play it. So it's a graph and a dashboard. So that's the dashboard thing. And if you're interested in that bit in particular, feel free to reach out. But it's all on GitHub now. Actually, we just last week put the pre-release out. So it's completely stable, but pretty good. So feel free to play around with it. And then there's this big question, which is to say, measuring is a great thing. Does it actually make any difference? Or not? And so we thought we'd test that. And so Christina, who is a postdoc in my team, is working on that at the moment. And what we're doing is basically deploying the dashboard and similar interventions in a bunch of universities, collect data, and see if feeding carbon footprint back to scientists make them embrace more sustainable computing behavior. Do you test on smaller scale? Do you have like less carbon going into wasted jobs, for example, or failed jobs or things like that? So we haven't like completely launched it, but we're basically going through ethics and everything at the moment, and hopefully we'll have some interesting answers for this. Now, does it work? Because remember, I'm not talking here about estimation. I'm not talking about measurements. I'm talking about estimation, right? We assume we can have a guess of the power requirement of a job based on things like runtime and power usage of CPU and things like that. And we make a lot of assumptions there. A lot of them we know are wrong, but we kind of have to do them. But does it give sensible results? It turns out that very early on, so 2021, Google tested us because we published our calculator and they were very unhappy with us for raising the topic. And so actually, you've done something right as a PhD student when you get attacked by Google on Twitter. I was like, oh, that's peak achievement. So they have access to the machine and they could put watt meters behind them. So they actually can test that. And they did it. So the graph here is from their paper. We're only looking at the green bars, which are our green algorithms tool. And that's the bar represent the ratio between the predicted value and the real power they measured. So we want the bars to be as close to 1 as possible. First, let's be nice to our calculator. The ones I've circled here, incredibly accurate, right? Based on the assumption, if you had told me the tool is wrong, is like 10% from the real value, I would be like, it's great, right? I'm not predicting up to the exact grams of CO2. As long as we're within the right order of magnitude, I'm pretty happy. So these ones, they're within like 2%, 5% of the real value. This is absolutely amazing. So we're actually a lot more accurate than I thought we would be on these ones. Obviously, and there's one in the middle at 0.08, which is also really good. Obviously, what Google wanted us to focus on here was these ones and saying, look, this is absolutely horrible. They're very far from the reality, massively overestimating carbon footprint. First, we just double. Are still the right order of magnitude. It's not great, but it's not terrible. I wasn't like losing sleep over it, but they were very, very upset by that. But I wanted to understand, why are we doing so well in some cases and so badly in others? So let's look at the ones we're not doing very well on. So the one we're doing well on are the P100. So each column is for a different type of GPU. So the P100 or the V100, these are NVIDIA chips that are sold publicly by NVIDIA, just happen to also be available through Google Cloud. But you can buy them. The ones we don't do very well on are the TPU. TPU are Google's very own AI chips. You can't buy them. The only way to use them is to use Google Cloud. And when a manufacturer sells a GPU, they have to release a metric called traditionally called TDP, thermal design power, but they have to tell you how much power it uses. The main reason is you need to know how much cooling you put in, because if they underestimate power, you either don't give enough power to it, not the end of the world, or you don't provide enough cooling and then you burn your house down. So they can't really mess around with this thermal data. So NVIDIA, you can find this power consumption on their spec sheet, and this is the data we use to estimate power usage. Google don't sell their chips, so they don't have to tell anyone. And basically, the TPU values we used were like some kind of random guess or like rough estimates. So the only thing this graph is showing is that when manufacturers are transparent about power usage, the calculators work incredibly well. When manufacturers are hiding power usage, the calculators don't work very well. I'm okay with that. That's fine. Interestingly, since then, Google have actually released the power metric for their TPUs. Maybe a little bit tired of people overestimating those. But yeah, so well, what's funny is this graph is clearly not showing what they wanted to show. And actually, it got removed from a subsequent archive update. But thankfully, archive keeps all memory. And so this graph is safe. But they ended up removing it. Slightly more robust benchmark done by a team of academics in France, where they benchmarked, again, different tools. So GA is our calculator, CC is Code Carbon, the other ones are a bunch of other tools. Right. Okay, the bit I'm happy with, so we want the green bar, which is the estimate, to be as close to the blue bar, which is the power measurement from the wall. If I wanted to show off, I would say we are the most accurate one on the GPU. We have like the closest green bar. In practice, it doesn't matter, right? They're all roughly the right value. Which one is most accurate probably depends on a few things, and it doesn't really matter. It did make me happy, but it doesn't actually matter that much. So that was pretty good. But the bottom row is all GPU benchmark. So we're doing very well. And we kind of knew that from the Google paper, but that's great to see that reproduced. We have to be honest and look at the top row as well, which is CPU benchmark. And you'll notice the green bars are a lot further from the blue bars there. And that means we tend to massively underestimate power usage on CPU benchmarks. And that's because CPUs are really hard. Like a GPU, really, you load, especially for AI, you kind of load it, and provided you kind of calibrated your model well, the GPU will be at 100% throughout until you don't. So it's very stable power usage. CPUs, they start working, they stop, it's kind of chaos. And because it's chaos, it makes estimating it from very simple metrics very hard. And that's actually something I'll show that in a minute we're working on now. But yeah, we have problems with CPU and we need to improve that. And actually, I've got a brilliant postdoc, Jack, who started in my lab recently. So that's actually an actual picture of what he's built. It's a bit like a kid in a candy store, just like building our own computer. It's brilliant. It's actually really hard to find data or benchmarks on that. So we're just building our own computer. The principle is quite simple. We've got under the bench here, well, under that is the power unit. It all goes through an interface which captures what power goes through every single cable. And from that, it goes into the actual computer. So it replicates a standard server system. So we've got a CPU. The GPU is not on there yet, but it's going to go there. We've got some memory, and the green thing is the motherboard. And basically, the black layer you can see in between here is the interface that intercepts everything, measures it before it goes through. And that's actually brilliant because we can get really refined measurement and actually understand how much power goes into the CPU and the memory and the GPU at any given time. So yeah, having great fun doing that. And hopefully we can improve these power models I was highlighting before, and also understand if some of the assumptions we're making are still legitimate or actually a little bit rubbish. So testing these assumptions is the first thing. The other thing is testing workflows. And if anyone here is interested, feel free to reach out, because we're testing a bunch of workflows, basically running them and seeing where the power goes. But if you have scientific workflows in your research that you think, oh, that would be quite fun to see where the power is going, should we spend time optimizing memory, or should we spend time optimizing CPU, GPU usage from a sustainability perspective? That's a very legitimate question. And that's the kind of thing this test bench could address. So if you're interested, same thing, send me an email, and we can touch base on that. Right, should we do anything about it? We tried a few years ago. I'm not going to spend too much time on this bit, but we created these greener principles. It was mostly just a way to say, okay, what are the different aspects we need to consider in computational science to make science more sustainable? And there's governance and responsibility. Who can make a difference? The answer is kind of boring, everyone, but in different ways. The importance of estimation, not focusing just on energy usage, potential collaboration, and the importance of education and research. So it's kind of, I'm covering a lot of that in this talk already. So there are two groups here, and a lot of people in the middle who don't really know. But on the no side, you're not going to be terribly surprised that, well, that's what's hard with big tech. They're doing great stuff for sustainability in terms of optimizing data center operations, because it aligns with financial interest. They're really at the cutting edge. Their data centers tend to be the more energy efficient in terms of cooling. Microsoft did this thing where they put a data center underwater. That was quite fun. They basically sealed it. No one touched it for a year. All maintenance had to be remote. Very little share of the hardware actually failed. It worked completely fine. Would make me slightly worried if I was a tech support engineer at Microsoft, but actually it worked fine. But then they said, oh, it was too expensive, so it just stayed a trial. They never actually deployed that. So there are lots of industry-led efforts on sustainable computing that are great and should be commended. Problem is, it doesn't really translate on their AI team. So all their big names in the AI team have taken this weird position, not only of saying AI's benefit will outweigh the environmental cost. I probably disagree, but that's a debate we can have, of saying AI has no carbon footprint. That's kind of the uniform position there. So you can see these 2022 was just before kind of ChatGPT and everything, just for context. But yeah, the head of AI at Facebook was saying, oh, absolutely no carbon footprint there. The carbon footprint of machine learning training will plateau then shrink. That hasn't aged terribly well, but that was their prediction. Quite disappointing. Yann LeCun, you may be familiar, one of the Pope of deep learning, created computer vision to a large extent, or at least convolutional neural networks, who said, total BS, completely useless, blah, blah, blah. He actually has a vendetta against the French researchers working on sustainable computing. So there's a research group, national researchers, so kind of all tenured faculty kind of style, calling them, what's the name again? Medieval obscurantist. Anyway, the problem of that is it makes it really hard to convince then younger researchers coming up that this is a problem we should probably think about when you've got these big names unleashing at it. But all of that is in the context of Microsoft carbon footprint jumping by 30% over 3 years, Google carbon footprint 50% over 4 years. And these are companies that were on sharp net zero trajectory. So this whole like plateau and shrink doesn't work terribly well. All because of AI. I was kind of expecting them to say, therefore, we will rethink our use of AI to align with our net zero target. They didn't. The main thing is they deleted the net zero pledge. That kind of solves the problem, I guess. You can't fail the target if the target's not there anymore. But they did that at the same time that they deleted their commitment to not use AI for military purpose. So there seems to be a little bit of shift of values at the moment. We don't have to despair. There is a yes side. And actually, research funders are very aware of the environmental impact of research, computing in particular, but not only computing, all aspects of research. This Heidelberg Agreement is national funders across Europe. It includes UKI for us here, coming together and saying, we cannot risk doing nothing. We have a responsibility regarding the carbon footprint of the research we fund. We've got the Concordat in the UK. You're probably familiar with that. The Horizon Europe, for one of their programs, they now have a green charter with a whole thing about AI, which is quite interesting, worth a look at. France started to ask environmental impact statement for people who apply for national funding calls on AI and climate. They say, if you're claiming your AI is saving the planet, you have to prove why it's not destroying it at the same time. Sounds fair enough as a question to ask. And actually, we work together because all the estimates have to be obtained with the Green Algorithm Online Calculator. So it's kind of a way of saying, you may all be wrong, but at least you'll be wrong the same way, and we can compare you. So let's think about what we can do about it. One is to actually build AI we need. We have two ways of building AI. We can identify a problem and then try to find the most resource-efficient way of solving that problem. Or we can find a new toy and desperately try to find something useful to do with it. The figure on the right is the Microsoft marketing about Copilot. And they say, look, these are all the places we can put Copilot in. We haven't found a single useful use case of it, but please, once we've put it everywhere, if someone finds it, let us know. And from a sustainability perspective, it's kind of a crazy, and even financial perspective, it's kind of a crazy way of doing it, right? They don't really have a problem. They just say, we're going to put Copilot everywhere. Let us know if it works. We've got this problem on the left. It's about how much, actually so much of OpenAI spending still goes on research and development. And it's interesting because it shows that AI is not demand-driven at the moment. It's not there's a need for AI and therefore companies are feeling this need. It's entirely supply-driven. They provide more and more models and kind of floods the market. And from a sustainability perspective, it's really hard because this idea of saying, well, if it's useless, people aren't going to use it. Well, it doesn't matter if it's not demand-driven because people don't use it. It doesn't matter. The tool's still out there. Again, example of, I don't know, Gemini, for example. Being transparent is an important thing we can do. So some people, we started it and other people did it, started acknowledging carbon footprint in their papers, which was really interesting. NeurIPS, the AI conference, started saying, we encourage you to track the carbon footprint of the models you present, especially because in AI, where it's all Python and there are some Python packages doing it, it's really easy. It's really not that hard. And people who submit at NeurIPS know they're going to submit at NeurIPS because they always submit at NeurIPS. So, it's easy to plan ahead and actually deal with that. If anyone has any insight why it got deleted, I am so curious about it. I don't know why, but they apparently thought it was too much hard work, and so now it's not there anymore. But that's a shame. We can use scheduling. So, carbon footprint varies over time a lot, and so you can actually, you can see this variation here. And actually, sometimes we don't need our job to run now. They can run in 12 hours when more renewable energy is available. Or they can run in Scotland where there's more renewable, and actually we don't need everything to run in the south of England. So this shifting, either spatial shifting or temporal shifting, are actually quite a nice opportunity for constant need of electricity, actually reduce the carbon footprint of it. If you're interested, we've got this side project we did years ago that's still going called CATS. So basically in the UK, you say, I have a job for 12 hours, and it gives you the best window in the next 3 days to run that based on the carbon intensity API. And I'll just finish with cultural change. I was not planning to do that, right? Right, here we are, sorry about that. Because we got this rebound effect. A rebound effect is this idea that you make something 10 times more efficient, people use it 100 times more. It's great for innovation. Slightly less good if your goal was to reduce energy usage. You make a highway twice as large to reduce traffic jam. You don't reduce traffic jam. You just get twice as many cars on the road. You make a data center twice as energy efficient. You don't reduce the compute we do. You just get more compute out of it. And we've got this paradox at the moment, which over the past 30 years, computing hardware gets more energy efficient every single year. Data centers get more energy efficient every single year. And the energy usage and carbon footprint of the sector grows every single year. So clearly, all these arguments saying energy efficiency is going to solve it, that's not going to work. That has never worked in the history of humanity. Rebound effect have never been beaten otherwise than taxes or quotas. So efficiency has never worked. It's not to say efficiency is bad. You know, we can combine that with other intervention and actually make things more efficient is good, but it can't be the sole solution. And remember, we're aiming for 45% decrease, not doing 45% more with the same budget. So one thing we tried to do is to build a community around that, to give a place for people who are interested in that, not saying working on that, just saying I'm kind of interested on the carbon footprint of my research, to have a place to ask questions and share best practice. So we created this forum. It's a classic forum, a bit like Stack Overflow, although it's for people who still remember Stack Overflow. You can go on there, but even without going on there, you can sign up to the newsletter, and I've got someone in my team who every month basically aggregates all the cool stuff published on the forum and send out a newsletter for people who don't actually check it out, which is fair enough. I've talked a lot about calculators. They're not the goal. They're just a tool to reduce this carbon footprint, but it's kind of worth remembering it. I like the way the whole society put it, where they say digital technologies developed and deployed, the same pursuit of net zero, I would actually ditch it, must be energy proportionate, which means they must bring environmental or societal benefits that outweigh their own emissions. That's not a crazy concept, right? In science, we should build stuff that improve society. It doesn't mean to improve the climate, right? It can improve society in many different ways, but we should have a reasonable expectation that what we're doing could eventually improve society. You know, some is more fundamental research that doesn't have direct application. That's fine. We still should have this reasonable reasonable expectation. And this idea of cost and benefit, because really that's what we're talking about here, it's made even more complicated when we realize that, you know, the new tools we build, the new robotic arm, the new MRI technology we develop, the code we write, all the data centers we built, they will benefit the least the population who are at the forefront of climate change, right? Population often in low-income country who are most hit by climate change will not benefit from the latest generation of Amazon smart speakers. And so it's fine to think about like a global level of cost and benefit, but we can't only think about this global level. We have to acknowledge that actually there are some very real local discrepancies. If you're not aware, there's this initiative in the UK called NetDrive, and it's basically supported by UKI, and the goal is to create a network across the UK, again, of researchers not necessarily working on sustainability, but aware and interested in sustainability. They have regular meetings. The next one is in a couple of weeks in Oxford. Might be next week in Oxford, actually. But they've got regular meetings. They try to put resources together. I think there's a mailing list coming at some point. So if you're interested, you can check that out. And a bit last minute, but we've got a conference. So we thought normally sustainability is a sidetrack. You've got an AI conference and it will have a sustainability track, or you got a neuroscience conference with a sustainability track. And we thought, can we flip the script? Can we have a sustainable computing conference and we can have an AI track and we can have a neuroscience track? And so we're doing that. We're organizing it at CERN in Geneva. It's going to be the first week of May. It's hybrid. So, I mean, you're very welcome. You can register until today's Tuesday. So you can register until tomorrow if you want to go in person. Registration online will stay open longer. But if you're interested, there's a very cool program coming up on that. So yeah, happening there. And I'll just mention Green DiSC, and we can take it up in questions. I'm just mindful of time. Wet Lab have been very successful at tackling the carbon footprint of their research, much better than us. partly because they see the impact. They see the chemicals going down the drain. They see the big freezers in their office. They see the single-use plastic they throw away all the time. We don't have that. Our data centers are halfway across campus, and you can start 100 GPU from your phone without even overheating it. So it took us a little bit of time. But one thing Wet Lab did really well is to have certification scheme, where it's basically a roadmap. Think of it like Athena's One, but for sustainability at group level, where you don't really know where to start, but someone says, well, if you do all this, you get a bronze certification, and if you do all of that, then you get silver. So they're really good as a roadmap. And after fighting it for a little while, we ended up creating that, so we called it Green DiSC. We did it with the Software Sustainability Institute, which is actually hosted at the University of Edinburgh, so it's based with EPCC. And it's free, it's open access. Basically, you get a list of criteria you can do as a research group to get the bronze certification. And it's been really, really interesting because we were actually the first free certification for sustainability, which sounds a little bit crazy. But all the other ones are behind paywalls, which sounds insane. So we made it all open access, and now there's a bigger movement for cross-domain free certifications. But if you're interested, just check it out. All the criteria on GitHub, but you can, they're quite straightforward action, especially for bronze, and then you get some peer auditing to get the certification. You can do it as a research group or as a central computing. I'm not going to go into details. Again, all the info on the website. It's kind of boring. And you get a nice certificate once you get it. The plan does not come with the certification. So yeah, great work here from Annika and my team who leads that. And yeah, so I can't thank everyone because it's a lot of work. I've tried to put pictures of all the brilliant people who are doing all the work. I'm just presenting it really here. Great team. And yeah, lots of good funders supporting that. And I think we have some time for questions. Thanks.